Okay, hello everyone. Got a couple more people coming in. We're going to be finishing up the thermochemistry chapter that we've been working on for the past 2 weeks now. Just have a little bit left, enthalpy of formation, and then some thermochemical nomenclature, or not nomenclature, thermochemical equations, working with mole ratios. That second part won't be specifically in the lecture notes, but I still want you guys to be able to do it. So we'll do a couple examples of it. Okay. So last time we had gone over how enthalpy is a state function, so we can sort of sum all of the individual steps together to get the overall enthalpy from reactants to products. So we're going to add on to that, looking at this thing called enthalpy of formation. So the enthalpy of formation, and it will be denoted as delta H with a little f next to it, is the enthalpy change for a reaction in which we're making a compound from its constituent elements. So if let me give you an example here. All of these are going to be in relationship to 1 mole of the product. All right, so if I have something like sodium combining with chlorine to produce sodium chloride, this product needs to be in 1 mole and everything else needs to be divided down or reduced down so that this is in relationship to 1 mole. Okay. Another example, if I had something like, let's say we're making NH3, I would need the corresponding individual elements to be reduced down so that we are only producing 1 mole. So it would be a half of an N2 and 3/2 of an H2. I'm not going to be having you guys do this part here, but I do want you to know that it is in reference to 1 mole. That does make a difference because when we're looking at our equations, if there's more than 1 mole of one of these things, we've got to multiply it out. So where are those enthalpy of formations? Well, they'll be in an appendix or the values will be given to you. And they are set at standard conditions, so 25 degrees Celsius and 1 atm. So here are some of the delta H of formation for common compounds. Again, if you are in need of enthalpy of formation, it is appendixed in the back of the text, but you also, let me pull it up here. We also have it stashed in our Moodle page. So the heat of formation. Okay. So you may want to have that accessible when you're doing your exams or homework. So if we look at this thing here, we've got the combustion of propane to produce CO2 and H2O. Now, when we were looking at Hess's law, we were able to break it into incremental steps, but what we're actually going to do here is we're going to extend or add a step. So I have my initial reactants. They're sitting here, and what we do is we're going to break those down or decompose those into carbon, hydrogen, and oxygen. So we've taken what is the propane and we've broken it down. So this is actually, it's not we wouldn't use the heat of formation of this. It would actually be the reverse, right? Then we can see that we take our carbon and our oxygen and we form CO2. And then we can take the hydrogen and the oxygen and form the water. So instead of going from our reactants sitting right here, straight down into our products, we decompose them into their individual elements, and then we recombine them into our new products. So what we're finding is that these sort of larger, more complicated equations are actually just a series of breaking down and then reforming. And if we know all of these delta H of formations here, we can break our equation down into simpler things, then we can actually have just a really, really basic equation that tells us the products, the delta H of our products minus the delta H of our reactants is the delta H of the overall. So here is the equation. It looks scarier than it is, okay? All we're saying is that the products minus the reactants. This is a summation symbol. So we add all of the products. We subtract them by all of the reactants added together. And then you see the little n and the little m that they have here. Those are the stoichiometric coefficients. So if I have, for instance, in that last equation, we had produced, 2 moles of water. I would need to multiply my formation of water by a factor of 2. And it isn't reactants minus products. I see that happen a lot with students. So make sure you're going products minus reactants. And we're not adding them together. We're finding the difference of those two. So let's see how this thing applies in a real equation. Here it is again. So we've got products minus reactants. If the delta H ends up being positive, endothermic, negative exothermic, pretty consistent. This is an important thing to note. Your formation or your delta H of formation of any element is 0. Why? Because it's already in elemental form. We can't form that. We're not using any sort of formation to get hydrogen by itself. This is true for elements that are in atomic form. It's also true for diatomics. So if I had something like Cl2, the delta H of formation is going to be 0 for this. Any element, it's going to be 0. So sometimes the delta H of formation isn't given for the individual elements. It's assuming that it's going to be 0. So when looking at this equation here again, we're going to take products minus reactants. So we would need to look back at that delta H of formation sheet. And we've got, this is how much energy, negative 393.5 kilojoules, is released for every 1 mole of CO2 that's formed. Now there are 3 moles being formed here, so we need to multiply it by 3. With our water, doesn't produce quite as much energy, negative 285.8 kilojoules. That's pertaining to our water here. And again, we have to take into account that there are 4 of those. So this is our products here. You can see that we're adding all the products together. So if you had 16 products, you would have 16 things to add in that first component. Then I'm going to kind of bracket this out even more dramatically. Then we're going to subtract by our reactants. Okay, as far as the reactants are concerned, our propane, we've got negative 103.85 kilojoules, and there's only 1 of those. So we will just put a multiple of 1 on there. This right here is an element, or it's in elemental form. So we know that value is going to be 0. They still put the 5 factor in there just so that you can see what's going on, but obviously this is going to be 0. So really, whenever there's an element, you can almost just ignore that. All right, so we can sort of ignore this whole thing. And we're really going to take these two values times their coefficients and subtract them from this value here. Does that make a little bit more sense what that equation was saying? The equation is a little funky looking.
So why would we not consider the element? Why are we not considering the oxygen?
We're not considering the oxygen because any element, its delta H of formation is 0. Because how are you forming it? It's an element. It's already formed, right? So any of the elements we can consider 0. Any other questions on that setup or how this actual example is relating to that previous equation?
Did you say if that table is in our lab anywhere, or doing
is in the lab manual? I don't think it's in the lab manual. It is in your textbook, but it is also on Moodle. Okay, so you can pull it off of Moodle too.
And we don't have to have it memorized, correct?
No. I would not expect you to have those memorized. Yeah. Those values would be given to you or you'd have the appendix, okay? So when we run through this, let me clear out some of that junk there. We end up with, an overall negative value of these two minus a negative value. Now remember, when we subtract a negative value, what is that? That is actually addition. So just make sure you're plugging that into your calculator correctly. And I guess it doesn't have the answer here. Find it out. We find, no, I don't like that. Should get a value of negative 2219. This is all addition and subtraction, so we would go with the lowest decimal place, 9.9 kilojoules. And again, it doesn't matter that, with our reactants, we're here and then products are here and we're going like this. It doesn't matter that we go up to decompose and then come back down to formation because again, this delta H is a state function. So we can do all sorts of crazy stuff to it because they'll all end up summing up. So let's do, have you guys do an example of this. Got one on a set of notes. Did that one. So let's look at this one here. Calculate the delta H at 25 degrees Celsius for the following reaction. So we have Fe2O3 solid plus 3H2 gas produces 2 Fe's, 2 irons that are solid, and 3 H2Os in gaseous form. And you can see in this problem, it gives you the delta H of formation. So go ahead and set the equation up, products minus reactants, and make sure to take into account the coefficients. All right, so I'm looking at all of this here. We're going to take our products, these two, and subtract it from the reactants. So this first product is an element. So I know that I'm going to take 2 and multiply it by 0. I can assume that it's 0 kilojoules. I'm going to add that to the water, which is 3. And we can see water's formation is negative 241.8. And let's put kilojoules in here. Kilojoules. Okay. We have, this is our product side. Now we're going to subtract that by our reactants. So the first reactant is this thing here, this one, iron 3 oxide. And I only have one of them. So 1 times the negative 824.2 kilojoules. I'm going to add that to the second thing, which is elemental hydrogen. So we've got 3 of them, and that's going to be 0 kilojoules. And so we can sort of just, ignore these things here. And when we run this through our calculator, we end up getting a positive number. So 98.8 kilojoules. Any questions on that? It's not too bad. It isn't too bad compared to the calorimeter ones. I think it's not bad. If you are seeing your delta H's and you're like, there's not enough delta H of formations given to me, how am I supposed to do these? They're probably elements. You can just ignore them. Are those zeros or O's? Those are zeros. Yeah, I know it looks like OKJ. They're 0 kilojoules. Let's do, where are the zeros coming from? So again, anytime that there's an element, I know that the kilojoules are going to be 0. That's an assumption you have to make. Okay, so all elements will have 0 kilojoules. Where are the zeros that aren't? Where are the numbers that aren't zeros coming from? Right here. And if they aren't given to you directly there, they would be on an appendix for delta H of formation. Oh, okay. Hopefully that helps. We'll do another 1 or 2 of them, okay? Let me pull out my other sheet here, yeah. Okay, we'll do this one here. So that looks like C6H12O6, looks like sugar or glucose. So I believe this is the combustion of glucose. So go ahead and do this delta H based off of knowing the formations. And you don't have to reference, everything you would need is right there. So for this one here, we start always with our products. So I've got CO2 and I have 6 of them. So I'm gonna put a 6 on the outside, and then my CO2 formation is negative 393.5 kilojoules. Okay, we don't have to include the mole because we're assuming that it's a kilojoule per mole. We're using 6 moles of it. So that's coming from here. We are then going to add our second thing, which is water. We also have 6 moles of water. Our water's over here, so negative 285.8 kilojoules. Again, we don't have to include the mole because there's 6 moles, those will cancel out. So that whole thing is a packet. We're gonna, once we solve that, we're gonna subtract that from all of our reactant stuff. So we've got the glucose formation, and we only have 1 of those. So 1 times negative 1273 kilojoules. And then we're gonna add that to oxygen, which is elemental, so it's gonna be 0. So we don't have to do a whole lot, 0 kilojoules. Okay. So plugging that into our calculator, in this case, we do end up with a negative number, negative 2802.8 kilojoules. Okay, so any questions on where any of those numbers came from? No, feel good with that, okay. Just for make sure you're doing products minus reactants, and you can ignore the elements. All right. The last thing that I want to talk about, which again wasn't in the slides, is thermochemical equations. So when you're given an equation and you have a delta H, that delta H is stoichiometrically related to all of these things. So I can write a couple conversion factors when looking at, sorry, give me a second. Here we go. Okay. So I know, like, looking at this, hey, 2 moles of Mg will produce 2 moles of the MgO, right? We can say 1 mole of the O2 will produce 2 moles of the MgO. So there's this stoichiometric relationship between all of them. Well, that same stoichiometric relationship applies to this delta H as well. So every time I use or combust 2 moles, sorry, let me, 2 moles of Mg, the amount of energy that is going to be produced is negative 1204 kilojoules. Another relationship, for every 1 mole of O2, for every 1 mole of O2 that is consumed, again, this much energy gets produced. And then finally, for every 2 moles of the MgO that gets produced, we produce this much energy, 0.04 kilojoules. So how much heat is released when 0.500 grams of magnesium react? So a lot of times in these problems, the values will be given to you in grams. We don't have a relationship between grams of magnesium and energy. What do we have? We have moles of magnesium and energy. So the first step is that we're going to need to go from our given gram value, scroll this down a little bit, our given gram value, and convert that into moles. So we have 0.500 grams of magnesium. Grams isn't going to do me any good, so I need to get that into moles. So for every 1 mole of magnesium, it is, my periodic chart, 24 something. right, 24.3 grams of magnesium. So grams of magnesium will go away. And now we have a value in moles of magnesium. I like that because I'm trying to get heat released or energy released. Well, I can use this thing right here. This tells me for every 2 moles of magnesium, that much energy gets released. So the 2 moles is going to go on the bottom. And the energy, -1204 kilojoules, is going to go on top. The moles will cancel. What I see happen a lot with students is they won't put the 2 in. They'll just always relate it to 1 mole. That's not the case here. This is a 2 mole thing. If we were doing it for oxygen, it would be 1 mole. But in this case, it's 2 moles. So you always want to use the coefficient. So all of the units that we don't want will cancel out here. And we should end up with work done. This will end up equaling -12.4 kilojoules. So this is kind of nifty because now we can go from an amount of a material into an energy value. Or we can go in the opposite direction. We can go from an energy value and figure out how much of it we need. So let's try that out. How many grams of magnesium react when 1,524 kilojoules are released? So we're starting with our kilojoules. We have 1,524 kilojoules released, so it's negative. And this says, how many grams of magnesium? Well, I know for every 2 moles of magnesium, this much energy gets released, -1204 kilojoules. I'm not having to pull that out of thin air. It's right there. The relationship is right there. Now this problem says, I don't want moles of magnesium. I want grams of magnesium. So we're going to go one step farther and convert it into grams. Every 1 mole of magnesium weighs 24.3 grams of magnesium. This is literally just the flip-flop of this setup. Those cancel, and also the negatives will cancel. And we should get 61.54 grams of magnesium are produced with that much energy. We'll do another example of this, but any questions on how that relates to each other, how you can go from amount into energy or energy into amount, but there's that stoichiometric relationship. Okay, let's try one out, or you guys will try one out. All right, let's do, I want you to do 1 and 2. So I'm gonna give you about 7 minutes or so to work on this. So this first one, how much heat is released when 55.85 grams of oxygen gas react? And you're given the equation and you're given the delta H. And then you have another one here for a different combustion equation. Oops, I'm sorry. Just another 30 seconds or so. And we'll look at it. Okay, so in the first one, we're talking about, we're given an amount of oxygen. So that's this thing over here. And we want to move towards energy. So I start with my given value of 55.85 grams of oxygen. I need to convert that into moles because the relationship between this and this is a mole relationship, right? This thing says for every 2 moles of O2, I'm going to produce this much energy, kilojoules. So first thing is to get it into moles. 1 mole of O2 does not weigh 16. It weighs 32 grams of O2. This is talking about the diatomic molecule, so you got to make sure that you multiply that value out by 2. Then from there, we can use this thing. For every 2 mole of O2, we're going to get -8 O2 kilojoules. Make sure your values cancel. So there goes the grams and there goes the moles, and we're left with just units of energy. And in this case, we should get -699.9 kilojoules. Any questions on that first guy? Somebody's got their mic off.
Can you leave it at
What was it?
699.9, or does it have to be 700, -700?
Let's see. We've got the given information gives you 4 sig
Okay.
figs. I guess this is only 3 sig figs. It's fine. That would
Okay.
be fine. Again, my care for significant figures starts to decrease as the semester goes on.
I'm with you.
Yeah, that would be fine. Yeah. All right. Next guy, similar setup. It's just a different problem. So instead, we're given 96.2 grams of O2, but we have this new equation. So we need to convert this 1 mole of O2 into that's 32 grams of O2. Let's see what we got question-wise here. Why is it 32 for O2? Because O2 is 16 times 2. There are 2 of the oxygens. It's in the diatomic. I know it's one of those little details that like, oh, why did I get that problem wrong? I knew how to do it. And it's the 2, okay? So yeah, anytime you have something in its diatomic form, you've got to multiply it by 2. Just treat it like you would treat this molecule. If we were going to do the atomic mass for this one, we would do 1 carbon and 4 hydrogens. In this case, we're going to do 2 oxygens. The only thing here that's different is that we have a molar ratio of 3 moles of O2, and it produces a different amount of energy, -555 kilojoules. Sorry, my handwriting is horrible. And so this will be -166 -167 0 kilojoules.
I had a question.
Yeah,
What I'm doing wrong, but I'm not getting those numbers in my calculator, even though that's the equation I'm typing in.
hold on.
Did you divide by 3?
I don't think I divided it by 3. Yeah, I don't think I divided by 3. I'm just realizing that now. Yeah, that's my problem. That's all me. -556 and kilojoules. And then this one, let me just double check.
Because I got -6. Oh wait, never mind. I did get that. That one was right.
That one, yeah, that one I got right. The second one was wrong. Yeah, sorry. Yeah, make sure you're using all the numbers that you put into your dimensional analysis. Any other questions on thermochemical equations? So going from grams or moles into energy or energy into grams or moles. Obviously, you have the only way you can do it is if you have a balanced equation. So those equations will be given to you there. And the delta H is not something you would like make up out of thin air. Okay, I would give that to you as well. All right, well that wraps up chapter 5, the thermochemistry chapter. So if you have questions or there's something you want me to do another example of, I am more than willing to help. Otherwise, you are free to go for the day. Make sure you get your homework and lab stuff turned in, and then I will see you all on Tuesday. Your next test is not for, I believe it's 2 weeks from this Sunday. Okay, we've got another chapter to go through. So yeah, you guys are free to go. It's good seeing y'all. Let me know if you have any
Thank
questions.
you.
Bye.